done. I guess I should say this for the future people. Hi, future people. Welcome to your free GMAT prep hour. My name is Reed Arnold. I will be guiding you through the wonderful world of the GMAT. One of our attendees has just requested that I demonstrate the flip the difference tactic. Now, I'm not entirely sure what that is, but I have a suspicion. So let me see if this is what you mean when you say flip the difference. Do you mean something like, if I have x minus y, let's say I have something like -4 over x minus y, I can turn that into 4 over y minus x, because I flipped the difference here and I lost that negative. Oh, bad circle there with the mouse. Yeesh. I undo. Oh, I can. Nice. Negative. Let me see if that's kind of what you were thinking. Pull up my chat box. Flip the difference of strategy for weighted averages. You missed Manhattan, the class 7. Jennifer, stick around a little bit after the recording. I want to make sure I know exactly what you mean, but that might be a little bit more of a lengthy lesson compared to what I have for this, but I'll be happy to help you out. All right, guys, I'm going to go ahead and erase this, clear my drawing, and we're going to stop sharing a whiteboard. Okay, I think I'm going to share, my desktop probably. Today we're going to talk about number properties and divisibility, because I know that is something that students struggle with. It's something that's weird on the GMAT. It's not something that most people are used to dealing with in the way that the GMAT requires. It comes with certain rules and ideas that people just aren't quite used to seeing. Okay, so I'm going to share with you my slideshow that I've made for this. If I can figure out how to do that. Here we go. All right, now we're cooking. Go ahead, friends, type in the text box. I just want to make sure you can see this. Can you see the free GMAT prep hour in my face here? June 26th, Reed Arnold. Put that chat. Sound good. Okay, cool. All right, guys. So just a quick little advertisement. This is free, but you can come try other free things. You can sit in on our class 1. That's 1/9 of a GMAT course for free. Find either online or in person. Try it out. See if you like the instructor. See if you like what we got going on. You can also try out our interactive course. That's a video course. Adapts to you as you go. It's an award-winning system. It's a really, really neat video course, actually. Here's what I want first, guys. I'm going to pull up a picture. Okay. Should be a bunch of colored circles. And what I want you to look at this for, a minute or so. And I want you to see if you can decode what this picture is showing you. Okay. Go ahead and type in the chat box if you think you know what this is, what it's showing, what it means. So Winnie is noting that orange is divisible by 2. and that the greens are divisible by 3. Ben is saying that the colors represent the factors of those numbers. Ben's pretty close. You're all pretty close. It does have to do with divisibility, as Amber and Brooke have said. Ben, so if it represents factors, and Winnie, you said the orange is divisible by 2. Why do some of these oranges, why do they have several slices of orange, whereas some only have 1 slice of orange? Same with the purple. Winnie says 2 slices means 2 by 2, meaning that there are 2 2s. Winnie's onto something. Okay. So what these circles are, they represent the prime factors of each number from 1 to 100. Now, once you get to 11, we kind of start to cheat and we just use red and we put the little number underneath, all right? But Winnie is exactly right. Anytime there are 2 oranges in a circle, it's because there are 2 2s in the prime factorization. Anytime you have 2 blues in the circle, that's because you have 2 5s in the prime factorization. 2 purples means 2 7s. 2 greens means 2 3s. 3 greens here on 54 means 3 3s. This right here is, and yes, it is about divisibility. And this is actually, guys, the heart of much of today's lessons. If you can understand this chart deeply, you will understand divisibility in a way that the GMAT demands and asks of you. You can Google search this, just search prime factor circles, okay? Put it on your phone and study it on the subway, or when you're driving. Don't do that. But it's a really good visualization of some of the patterns that lie under numbers and how they divide and when they divide. And if you can understand this, and we'll come back to it, and we'll keep kind of pulling this circle back up. If you can really see how numbers fall apart and are built, then you'll be on a good path to understanding how the GMAT talks about divisibility. Okay, so what is divisibility anyway? A is divisible by B, simple divisibility sentence. How many ways, question for you all, how many ways can you say that exact same information, that A is divisible by B? Go ahead and, if you can think of another way to say the same thing, go ahead and list it. How would you say that A is divisible by B? I will type. Good. A is a multiple of B. Wonderful. B is a factor of A. Wonderful. Any other ways to say it? These are 2 good ones, but there are several others. Here's what I got. This is about all I could come up with. Okay, but they all mean the same thing. A is a multiple of B, B is a factor of A, B divides A without remainder. When A is divided by B, the remainder is 0. More informally, the GMAT won't use this, but B goes into A equals B times X, where X is an integer, A over B is an integer. It's all the same thing. It all means A is divisible by B. Okay, so first off, realize that. And whenever they give you one of these coded languages, realize they're telling you the same thing. Now, what does divisibility really boil down to? Hint, hint. Okay, divisibility really means, if A is divisible by B, it means that all of the prime factors of B are also prime factors of A. Okay, and so I want to demonstrate that okay, with just some quick examples. All of the prime factors of B are also prime factors of A. We all agree that, say, 75 is divisible by 25. Why? Well, 75 equals 5 times 5 times 3. That's the prime factorization. The prime factorization of 25 is 5 times 5. Okay, and all of the prime factors down here are also prime factors up here. And so those cancel out. Okay, we could say, oh, pick a nice random number. Let's say 162 is divisible by 6. Okay, well, 162 equals 81 times 2 over 6. And because I know my powers of 3 very well, I know that 81 is 3 to the 4th. So that's 3 to the 4th times 2, and the 6 is 3 times 2. So sure enough, all the prime factors down here are also prime factors up here. And then there's 3 3's left over. 3 cubed. Okay? That's what divisibility is every time. And I want you to start trying to think about divisibility in terms of this. I know it's going to feel a little weird. So you're just being like, well, I mean, 25 goes into 75. Isn't 6 goes into 162? I can do the long division, right? I can write out 162 divided by 6 and figure this out and yada, yada, yada. But actually, long division is generally not the most efficient way to work through a GMAT problem. In fact, we had a full free GMAT prep hour about avoiding long division. I recommend you watch that. Try to start thinking about this in terms of prime numbers and prime factors, because that will help you on harder GMAT questions that are harder than 162 divided by 6. Okay. Making sure that everyone's good. Cool. So let's go back to divisibility. Okay, so I want you guys to do the same thing with these problems here. I want you to show how these things are true based on the prime factors of the numbers, and how all the prime factors in the denominator are also going to be in the numerator. Okay, I'm going to go off camera for just a moment, give you guys a minute or two to work. Hey, that's weird. All right, friends, keep working if you're there towards the end. I'm going to start kind of filling in what I think, what this should look like in terms of prime factors. Okay, so 40 is 2 cubed, that's 8, times 5, over 2 times 5. All the prime factors in the bottom are prime factors in the top. Okay, 192. Divided by 48. Okay. Well, I could divide 192 by 2. Whenever I'm in doubt, I just divide by 2's. I realize that 192 is divisible by 3. No, not a line. I realize that 192 is divisible by 3, but I find it tough to do in my head, and I try to, try to do quickly, and I find it easier to just work in pieces. So that'd be 96 times 2, okay, over 48. And then 96, I realize, is 48 times 2. So that, again, of course, that would be enough to say that, okay, obviously 48 times 2 squared over 48 cancels out. But what is the prime factorization of 48? It's 2 cubed. I'm sorry, 2 to the 4th times 3 over 2 to the 4th times 3. All the prime factors in the bottom are also on the top. Okay, 350 over 14, 35 times 10 for 350, which breaks down to 7 times 5 squared times 2 over 7 times 2. 1144, 11 times 100, which is 11 times 2 squared times 5 squared, 44, 2 squared times 11. Everything on bottom's on top. This number 5 is a little bit weird, but what I was hoping you realized from this sentence is that J must have at least M A prime factors, at least N B prime factors, and at least P C prime factors. J can have all kinds of others, have infinite other prime factors. It can have more A's, more B's, and more C's, but it has to have at least the M, the N, and the P of A, B, and C respectively, because all the prime factors in the bottom have to be up top. Okay, 30 is a factor of 45 times 42. I wanted to show, to get the idea across, up here we've only been dealing with single numbers, but we can do this with products and strings of multiplication, which the GMAT will actually ask you to do in more complicated settings, but it's kind of the same idea. 45 is 3 squared times 5 times 11 times 2 for 22 over 30, which is 2 times 3 times 5. All the prime factors on bottom are on top. Okay, so any questions about this? Do we see how at heart divisibility is about the prime factors in the divisor being also in the number in the numerator? Okay, any questions? Feel free to jump out, shout out, scream out to the rooftops your newfound knowledge about primes. Maybe you knew this. I promise we're going to ratchet up the difficulty here soon. But I want to lay it down clear and simple first. Okay. ETS is asking a question about number 5, I believe. What's your question, ET? Can J be equal to A, B, C? Can J be equal to A, B, C? Do you mean A times B times C? Is that what ABC means? Well, it could be equal to ABC. I'll ask, here's a question for no, you're on your phone. Oh, God bless you. Dealing with a chat box on a phone must be a nightmare. So here's my question to the room. I'll ask everyone. I want everyone to think about this. She's wondering, he or she is wondering, if J is equal to A times B times C. All right. She's wondering, they're wondering, I keep saying she because I have a friend named EP, and so ET is, I don't know your gender, but forgive me. J equals A times B times C, and we're wondering if that's true. Okay, good, Shine. Yeah, so Shine is noting that that's true if M equals N equals P, and they're all 1. Okay, I mean, assuming that none of them are 0, which would be, I guess, possible, but I didn't mean to have that possibility. M, N, and P are all positive. And if they're all 1, then yeah, J could be A times B times C. And you would have J on top as A times B times C, and K on bottom as A times B times C. And every number is divisible by itself. So yes, it is possible, but it's a very special case, ET. Only one case where that's going to hold, and that's where all of those powers are 1. Okay. Okay. So prime factors, as you might know and as we might be hinting at, prime factors are the building blocks of all positive integers. Every positive integer greater than 1 is either prime or built by primes, a product of primes in the way that we were seeing on that previous exercise. Okay, they tell you everything you want to know about a number. And just to be clear, guys, the number 1 is not prime. Common misconception. It's neither prime nor composite. It's just 1. It's weird. But if it's not 1 and it's a positive integer, it's either prime or built by primes. And they tell you everything. So I picked a number at random, just 324. Okay. And I want you here on the right side, okay, here on the right side, go ahead and list the actual factors, not the prime factors, the factors of 324. And over here, get the prime factorization of 324. Okay. And then what I want is for you to take that prime factorization and see if you can't try to tell me as much as you can about this number. Okay. And here's a little hint. Try to make a connection. Didn't mean to move that. Try to make a connection between these two things, prime factors and factors. All right. Take just a few minutes to do this. All right, we'll come back and we'll talk. Okay, friends, you might be wrestling with the factors of 324. That's probably harder than the prime factorization of 324, but ultimately you'll get a list that looks something like this. Okay. You have the factors over here, 1, 324, 2, 162. The prime factor is 2 squared times 3 to the 4th. Just these two numbers as the prime factors. Well, what does this prime factorization tell you? What does that tell you about this number 324? Pretend you were just given that set. You were just given 2 squared times 3 to the 4th. What would you know about whatever number it was? It ends up being 324, but what do you know from just the prime factorization? Good. Shina says it's even. Think about, and Winnie says it's even. Think about how did they know this? How did they know it's even? Well, they see that there's a 2. Even numbers have 2's in their prime factorization. Good. What else could you say? Very good. How about it's a multiple of 3? If 2 makes it even, a 3 makes it a multiple of 3. And if it has a 2 and a 3, what must it be a multiple of? Good. Has to be a multiple of 6. And if it has 2 2's, what does it have to be a multiple of? 4. And if it has 2 2's and a 3, what does it have to be a multiple of? Good. So you'll notice, guys, that we're building these factors. We build these factors out of some combination of the prime factors. Okay, 9 gets none of the 2's. None of the 2's go to 9, but 2 of the 3's do. Well, that leaves 36, 2 of the 2's and 2 of the 3's. Okay, 12 gets 2 of the 2's and 1 of the 3's. Yeah. Leaving 27, which gets the remaining 3 3's. Okay, so you build the factors out of a number. You build the factors of a number out of the prime factors. Okay, now there's one other nifty thing about this prime factorization that I think is worth mentioning here. We know this number is a perfect square. Okay, in fact, 18 down here is the square root of 324. How do we know from the prime factorization that this is a perfect square? How does the prime factorization tell us it's a perfect square? Good, Amita. Everything's raised to an even power. Okay. In order for a number to be a perfect square, the prime factorization must have only even powers. If I try to take the square root of a number whose prime factorization is this, 2 to the 4th times 3 cubed times 5 squared times 7. If I try to take that square root, well, using my exponent rules, okay, the 2's fine, 2 to the 4th, we take the square root of that, we're left with 2 squared. The 5 has a 2, the square root of 5 squared is 5, so I have that. Then I'm left over here though, I still have 3 cubed and 7. They're stuck under the radical and they are not perfect squares. There's nothing that's gonna fix that. Okay, so the prime factorization can tell you if it's a perfect square or a perfect cube. If it's a perfect cube, all of the exponents need to be multiples of 3. Okay. So all the properties of your number are just tucked right there in the prime factorization. And if we go back to the prime circle chart, okay, I know the number 78. It's a multiple of 6 because it's got an orange and a green. It's got a 2 and a 3. Okay, so it's got 2, 3, 6. Let's look at a fun one. 60 is a fun one. It has a lot of colors. Okay, 60's got to be a multiple of 15 because it's got a blue and a green. And it's got to be a multiple of 10 because it's got a blue and an orange. And it's got to be a multiple of 20 because it's got a blue and 2 oranges. And it's got to be a multiple of 30 because it's got a green, a blue, and an orange. All these other things. And again, I know these are simple numbers, and I know this is a relatively simple concept perhaps, but it's still the way you should start to think about divisibility and factors and multiples and how it all boils down to primes. So, if you thought that was easy, let's ratchet up the difficulty. Okay. X is the product of 20 even, the first 20 even integers, and 35 to the k is a factor of x. So which of the following is the greatest possible value of k? I haven't presented the choices yet. I want you to think about this question. And I want you to think about it in terms of prime numbers. Okay, this is annoying. Think of it in terms of prime factors. Just out of curiosity, guys, can you see my mouse moving around the screen without that little spotlight on it? Do you see my mouse when it points to prime factors? Oh, that's so good to know. Thank you. Wonderful. So I won't need to worry about that spotlight. Go ahead, guys, and type out in the chat room what this question is asking in terms of prime factors. Think about what that looks like. So I know that X, China will be repeated at least 20 times and probably a lot more. Okay, I have X over 35 to the K, right? I'm told that 35 to the K is a factor of X. Adding up all the exponents of 2, not quite. The product of the first 20 integers is going to be 2 times, through our first 20 even integers is 2 times 4 times 6 times 8, etc., all the way to 18 times 20. Sorry, not 18 times 20, that's the middle. That's the first 20 integers. We got to go all the way to 38 times 40. 38 times 40. And we're dividing by 35 to the K. Now I know that 35 to the K looks weird, and 2 times 4 times 6 times 8 times 10 times 12, etc. It looks weird. One of the GMAT's favorite games is making things look weird when the same rules apply. Everything we were doing earlier with very simple numbers is still in play. Everything. It's asking the exact same question. Remember what divisibility really means. What does this mean in terms of prime factors? Should be something like all of the prime factors of blank are also prime factors of blank. What are those blanks? Should be all of the prime factors of 35 to the K are also prime factors of X, which is 2 times 4 times 6 times blah, 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 forever, until 40, not forever. All right, it's the same question. All of the prime factors of the denominator have got to be prime factors of the numerator. Okay, so with the rules being the same, even though it looks more frightening, GMAT's favorite games, they scare you with appearance. All right, don't be frightened by appearance. It's often the same simple rules. It just looks weirder. All right, if I think about this, well, the prime factors of all these numbers up here, 2 times 4, there's definitely a lot of 2s. We picked up on that. Even numbers are going to have a lot of 2s in their prime factors. I mean, 8 has 3 2s. 8 is 2 cubed. Yada, yada, yada. Over, well, what's 35 to the K? What's the prime factorization of that going to look like? What's the prime factorization of 35 to the K? So I'm going to type that out in the chat box if you think you know. Good, Winnie. It's going to be 5 to the K times 7 to the K. and I want to know the biggest possible value of k, right? Where this whole thing becomes an integer, meaning everything in the bottom cancels out. Okay, well, in order for that to happen, I got to think about how many 5s appear up top, how many 5s appear over here, and how many 7s appear up here in all these even numbers that are being multiplied. And the fact is that 5s and 7s are not as common up there as the 2s are. We have a 10, that'll give us a 5. We have a 14, that'll give us a 7. We have a 20, that'll give us another 5. We have a 28, that'll give us another 7. We have a 30, that'll give us a 5. We got a 40, that'll give us a 5. And then we got all the other things, the 2, the 4, the 6, all the other things that aren't going to give us the numbers that we really care about here. 5 to the k, 7 to the k. Well, this 10, again, has a 5. This 20 has a 5. 5 times 4. But I end up having quite a few 5s. You might notice. I have 5s with, it's not super common, but I got a lot more 5s than I got 7s. My 7s are rare. 7s are only appearing basically at the 14 and at the 28. 14 is 7 times 2. That yellow is not particularly convenient. 7 times 2. And the 28 is 7 times 4. Well, then how many 7s can I cancel out in that whole string of multiplication of even numbers? How many 7s go away? Or could go away? 2. That's all I got. I only got 2 7s in the prime factorization up top. So the biggest k that I can give you is 2. Can't get any bigger than that because it's not going to go away anymore. There's no 7s up top for the 7s below to team up with and cancel out. It's at heart, it's just all about the primes, guys. Seems to be more complicated. At heart, break down the numbers, think about the prime factors that matter. I'm asked about 35. Okay, well, what are the prime factors of 35? 7 and 5. Okay, I'm wondering about those numbers. Where do those appear up top? Only at these situations, right? Okay, all prime numbers. Any questions about that? See how it's just the same rule reapplied? Okay. Oh, it looks like I changed the number at one point from 35 to 70K, but it's the same problem there. Okay, here's another question, guys. Take 2 minutes and try to answer this one. And I know it looks nasty, looks tough. Think about primes. All right, guys, that might not be quite 2 minutes, but for the sake of time, because my God, it's going fast, I'm going to show you kind of how this is done. Now, a big sign that you should think about prime numbers, guys, is when you have big, weird numbers or big, weird products, like we saw in the last question. We have 4,200 and 42,000, and we're talked about divisibility, factors, multiples, division, divisibility. That's a good sign to check prime factors. So 4,200, okay, well, that's 42 times 100, okay? That breaks down to 7 times 6, which is 2 times 3 times 7. And 100, I have memorized, is 5 squared times 2 squared. Okay, so the final prime factorization here is 2 cubed times 3 times 5 squared, 5 squared times 7. I like to write prime factorization like this. It keeps it organized, put it in descending order, etc. Okay. So I know that I have a number m that's a multiple of this. Okay, it's either this number, because this number is a multiple of this number, or it's 2 times that, 3 times that, 4 times that, 5 times that, up to, it's got to be less than 42,000. Well, 42,000 is 10 times 4,200. Okay, so whatever number m is, it's either 2 times this, 3 times this, 4 times this, 5 times this, 7 times this, but it's not more than 9 times this. 9 times this number is as big as we can get. And you'll notice every time we multiply by a number, we steal those numbers' prime factors. Or I don't want to say steal, that's so negative. We add them, we would add them to the prime factorization of m, whatever m is. Okay? Well, the GMAT also, guys, it gives you hints. When you realize here that you're limited to 10x, to 10 times, and you realize that, hey, here's the prime factorization, and I can't go more than 10x, you might start to wonder about the next number that would matter, which might be something like 11. Okay, that prime factor 11 comes after 10. It's not already here. The GMAT does, it drops little nuggets like this, little clues. 11's not already here, and we're not going to get it because we can't multiply by 11 because we are limited to less than 10x. And so answer choice B clearly has a prime factor of 11. Okay, it clearly is 11 times 10, and that can't be a factor of this number because 11 can't be a factor of this number. All based on prime factors and some good GMAT clue picking up. That's the official way to say it, clue picking up. Okay, it's already 9:18, and I had so many more things to talk about. I might have to extend this to a second session at some point. What about 10 itself? Or do you mean what about 10 itself, ET? It was not allowed because I said strictly less than. So I could not do 10 times 4,200 and bring that into the prime factorization. Okay. It would have to be 1 through 9 times 4,200 and the prime factors of 4,200. So why isn't 750 an option? 750 is an option. Which of the following cannot be a factor of n? Okay, be careful. Always look to see if you're looking for exceptions or the actual the things that can't be or the things that must be or could be. Here I'm looking for things that just can't be factors. All the other ones could be depending on which prime factor you multiply by, or which number you multiply by that gives you certain prime factors. Okay. Okay. I think I'm going to skip ahead to the remainder cycle. I'm going to skip past greatest common factor and least common multiple, useful though they can be. This is much more useful and much more common. Okay. We're talking about so we've been talking about how like numbers that actually divide cleanly. For the last 10 or 15 minutes, I want to talk about numbers that don't divide so cleanly. Sometimes they still will. Remainders of 0 are a thing. Okay, but remainders are those things that are left over when you divide. The reason we are not so comfortable with remainders is because we haven't dealt with them since like 5th grade. You know, we first learned division, then we learned about remainders, and then we learned about fractions, and we haven't thought about remainders since because we stopped using them. We just used fractions and decimals instead. Remainders went by the wayside. But the GMAT brings them back, okay? And it brings them back for an interesting reason. Take a look at this lovely little picture again. All right. And this is, again, it's something that seems obvious, but pointing it out and showing how the GMAT tests it will be illuminating. Notice the spacing between the colors. You don't get another green color until you go 3 spaces. 3 spaces, 3 spaces. These are the multiples of 3, obviously, right? You don't get another blue color until you go 5 spaces. 5 spaces, 5 spaces, 5 spaces, 5 spaces. Remainders are the cycles in between those spaces, okay? The multiples of 5, so when you're dividing by 5, the multiples of 5 happen every 5 places, but so do the remainders when you divide by 5. As an example, I'm going to pull up the remainder cycle when dividing by 7, okay? If I divide 1 by 7, the remainder is 1. It's 0. How many times does 1 go into, how many times does 7 go into 1? 0 times, and 1 is left over. Same thing with 2. Has a remainder of 2. 3 has a remainder of 3. 4 has a remainder of 4. 5 has a remainder of 5. 6 has a remainder of 6. 7 has a remainder 0, because 7 divided by 7 doesn't have a remainder. 8 has a remainder 1. 9 has a remainder 2. 10 has a remainder 3. 11 has a remainder 4. 5, 6, 0. 1, 2, 3, 4, 5, 6, 0, forever and ever and ever. This is the cycle of the remainders of 7, and they always come in this order. In that cycle every time. 1, 2, 3, 4, 5, 6, 0. 1, 2, 3, 4, 5, 6, 0. Okay, here's a graphical visualization of it. Okay, when you divide by 7, you have 0, 1, 2, 3, 4, 5, 6. Those are the possible remainders. And in terms of 7, right, in terms of dividing by 7, 1 and 8 are basically the same. 8 and 15 are basically the same. They have remainder 1. 3 and 10 are basically the same. They have remainder 3. And 24, and 31, and 38, and 45, onward and onward and onward. They all have remainder 3. Okay, this is called modular arithmetic, if you want to nerd out and research it. Okay, it was one of my nightmares in college math. The GMAT doesn't go as conceptually ferocious as that course did, but it's something that we haven't thought about it ever. And so it's kind of weird to start dealing with it. But just realize that these remainders cycle, and every number that you divide by has a remainder cycle. Okay, the remainder cycle of, if I were to draw the remainder cycle of 3, which the GMAT does like, okay, it would look, I'd have a circle here. I can't draw, it's going to be ugly. Here's my remainder 0s. Here's my remainder 1s. Here's my remainder 2s. And then I'd have 1, 2, 3, 4, 5, 6, 7, 8. Okay, and these numbers would just cycle through, always, always, always. All right, and you can draw remainder cycles for any number. I chose 7 randomly just because I thought it was a nice visual. All right, now here's the thing about when you're dealing within a remainder cycle of a single number. So just staying with dividing by 7. There are certain rules that will always apply. When you divide by 7, a remainder 5 plus a remainder 2, whatever numbers they are, it does not matter, will always be a remainder 0 or a multiple of 7. So 12 plus 9, remainder 5, remainder 2, 21, multiple of 7. 33 plus 30, remainder 5, remainder 2, 63, multiple of 7. 705 plus 72, remainder 5, remainder 2, 777, a multiple of 7. Every time, no matter what numbers you pick. Okay, there are many other rules. These are just 2 examples. The product of a remainder 3 and remainder 4 is always a remainder 5. 10 times 18 is 180. It's 5 more than 175. 70 times 4 is 68. 5 more than 63. 31 times 11 is 341. I did the math. It's 5 more than 336, which is 48 times 7. Okay. As long as you're sticking with the same number you're dividing by, it doesn't matter which number you choose. So anytime you see one of those questions, that asks something like, let me find my text box. It'll say something like, if n has a remainder 4 when divided by 9, whatever it is. Just pick a number for n, okay? Because it's true, no matter what number no matter what number n is, it's going to have the properties that are required when divided by 9. So just pick a number, okay? If you're dealing with 7, pick a number that has that remainder when divided by 7. Now, here's kind of a neat thing. Do these rules seem at all familiar to you? I know these things are going to be a little bit different. These things are weird rules, and you don't need to memorize these rules, for God's sakes, please don't. But know that they exist in a remainder cycle. But there is a remainder cycle whose rules you want to memorize and probably have already started to memorize. Does anyone know what remainder cycle I'm talking about? Just out of curiosity. It's the remainder cycle of 2. Because the remainder cycle of 2 is what even and odd are. Even and oddness at heart is just about the remainder when divided by 2. We have special words for them, unlike we have for other remainder cycles, okay? But it's all just, you know, an odd number is a remainder 1 plus an odd number, remainder 1, equals an even number, remainder 0, okay? An even number, remainder 0, times a remainder 1 equals a remainder 0. That's even times odd equals even. Yeah, Shine, I'm glad you think that. It's a really interesting realization that most people don't really talk about. We just stick to our rules for even and odd and don't really ever connect it to divisibility, but at heart it's the same game. And it's important that you understand it for even odd, even if you know the rules really well and can just do it memorized, because the GMAT will ask about the remainder cycle of 3, which has, you know, we don't have special words for the numbers. When we have one extra remainder, we have remainder 0, remainder 1, and remainder 2. And again, you don't need to memorize the rules, but you want to know that they exist. And you want to understand that, you know, the types of number when divided by 3, it's very similar to the types of number when divided by 2. It's just that there's a third type. Okay. I think it's cool anyway, but I'm kind of a geek. Okay. So if k is an integer, let's talk about this real quick. If k is an integer, what do you know about k plus 1 and k plus 2 and k plus 3 and k plus 4 and k plus 5 and k minus 1 and k minus 2 and k minus 3 and k minus 4? P.S. Anytime you see numbers like this in a GMAT problem, especially if it's about divisibility or multiplication or something, it's probably about this remainder cycle in some way. We're dealing with the remainder cycle. So if k is an integer, well, you know that k plus 1, at the very least, if k is even, k plus 1 is odd, right? You know that. Okay, and k plus 2, you know, is going to be back to be even. And k plus 3 is going to be odd. That's the remainder cycle of 2. Ah, but what about the remainder cycle of 3? Well, we have a similar pattern going on. It's just a cycle of 3 instead of a cycle of 2. Okay, if I know the remainder when I divide by 3 of k, it's going to be the same remainder of k plus 3. And these two are going to be the other two types of remainders. I either have remainder 0, remainder 1, remainder 2, remainder 0, or I have remainder 1, remainder 2, remainder 0, remainder 1, okay, or the third option. I won't waste time doing it, but like it's, you know, a pattern, okay? Same thing if you go by 4, you know something about k and k plus 4. They have the same remainder when divided by 4. K and k plus 5, same remainder when divided by 5. Okay, and you can figure out relative to any of the other remainder cycles where they fall. K plus 2 and k plus 5 have the same remainder when divided by 3. Why? Because they're 3 apart. Right? And so you're like, Reed, why are we talking about this? Who cares? Well, so a few fundamental rules. God, it's already 9:30. Why is time so fleeting. Some fundamental rules about this, guys. If you have a multiple of x, whatever integer x is, a multiple of x, and you add another multiple of x, you end up at a multiple of x. That's basically the even plus even equals even rule for all remainder cycles, okay? If you have a multiple of x and you add not a multiple of x, you end up at not a multiple of x. That's basically the even plus odd of all remainder cycles. This one is different though. If I add two not multiples, on remainder 2, it gets me a multiple. That's the special case. That's why even and odds are nice. But on other remainder cycles, I just don't know necessarily immediately. I'd have to dig in more. So this doesn't have quite so many nice rules in the broad application. These are the most common ones that you definitely want to tuck away, and you can use them for number property games. So let's do a question. Let's try this one, guys. Try 2 minutes here, and this will probably be the last thing we do tonight, unfortunately, because time just went so fast. Okay, that's 1.5 minutes, and for the sake of time, okay, I'm going to just call that there. Why is this? Go away, recording alert. Okay, so this question, does the integer k have a factor p such that 1 is less than p is less than k, is really asking, is k prime? That's really all that's asking, is k prime? Right? If k doesn't have a factor p between 1 and itself, then it's prime. That means its only two factors are 1 and itself. So this question is just asking, is k prime? In fancy language, the GMAT loves to do that. We know this. All right, well, statement 1 tells us k is greater than 4 factorial, which is 24. So this tells us k is greater than 24, which is not particularly useful. There's plenty of prime numbers greater than 24 and plenty of not prime numbers greater than 24. That doesn't narrow down k that much. Well, 2 is definitely the tougher place. Okay, now just general guideline, if something looks tough, error sufficient. I would guess B if I had to guess and move on. But if you do some work based on what we just talked about in the remainder cycle and some of these rules that pop up, what do you know about the number 13 factorial? It's enormous. You don't have time to calculate it, and you need a big calculator. Okay, so, but what do you know about that number? 1 times 2 times 3 times 4, all the way to times 13. Think about what we've talked about today. It's a multiple of all those numbers there. 1, 2, 3, 4, 5, 6, all the numbers 1 to 13, it's a multiple of that. And we're told that k is between 13 factorial plus 2 and 13 factorial plus 13. Well, what do I know about this number 13 factorial plus 2? It's a multiple of 2 here. 13 factorial is, because it has a 2. And we add 2. So this number is even. Okay, so if k does equal 13 factorial plus 2, then it's even. And I'm going to realize that's true of all the even numbers that I could add to it. It's always going to be even, which means K is not prime because the only even prime is 2. Well, but then we realize something similar about the odd numbers, because 13 factorial is also a multiple of 3 because 3 is there and I add 3. That would be a multiple of 3. 13 factorial is also a multiple of 7 because 7 is in that product chain, 1, 2, 3, 4, 5, 6, 7. And I add 7 to it, I end up at a multiple of 7. 13 factorial plus 9. Every number from 1 to 13 gets me another multiple of whatever number I'm adding. So whatever number K is, there are 13 or 12 options, okay? But every one of them is not prime because it's going to be a multiple of a number plus that number, a multiple of 7 plus 7, a multiple of 5 plus 5. And so whatever it is, it's not prime, okay? So this is hinging on this understanding of how the remainders and multiples come through in a cycle and how you can add numbers to big unknown numbers. But if we know something about what kind of number it is, what is its prime factorization? What is it a multiple of? And we know what we add to it. We can figure out something about the properties of the number, even though I have no idea what 13 factorial plus 3 is huge. I have no idea what it is, but I know something about the type of number that results. Okay, that's based on divisibility rules, and it's based on my understanding of this cycle. A lot of number property questions will hinge on stuff like this. Okay, I would love to do one more question with you, but I'm afraid there's just not time. But I would love to take a second to wrap up any questions you all have that I can help you with. Anything you'd want to discuss or go through about what we talked about today. I know someone wanted to talk about a weighted average thing, which I'm going to go off recording for that because that's just not on topic here. But if there's any questions about divisibility, primes, and this cycle of multiples and remainders, I'd love to help you out. So the answer to this problem was B, okay? Because statement 2 is sufficient. We don't know what number K is, but it's not prime. Yeah, Shino, we'll find time to do LCM and GCF. They're not super commonly tested, so I wanted to get to remainders because they do pop up, I think, a little bit more. But you can use prime factors to solve for the least common multiple and the greatest common factor. Okay. Anything else, friends? Anything I can help you with? Otherwise, I'm going to go ahead and call it and end the recording. Okay. All right. Thanks for coming. I really appreciate it. Hope it was fun and informative. Hope you got some new things to think about and wrestle with and start to think about these numbers in a different way. All right. Yes, Amrish, the recording will be online. It'll be posted on YouTube along with all the other recordings we've done. So this will be the 7th in the series. We have more to come here in about 2 weeks. All right.